Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Coding 101 is provided by CacheFly at CacheFly.com.
This episode of Coding 101 is brought to you by Lynda.com, the online learning platform with over 3,000 on-demand video courses to help you strengthen your business, technology, and creative skills. For a free 10-day trial, visit lynda.com/C101. That's LYNDA.com/C101. And by Braintree. Even the best mobile app won't work without the right payments API. That's where the Braintree V.0 SDK comes in. One amazingly simple integration gives you every way to pay. Try out the sandbox and see for yourself at braintreepayments.com/coding. Today on Coding 101, we've got Smitty Halibut. He's coming on to play with lighting. Hello and welcome to Coding 101. It's the Twitch show where we let you into the wonderful world of the Code Monkey / Code Warrior. I am Father Robert Balliser, also known as Father Glows a lot. You may be wondering why I'm wrapped in a couple of layers of LEDs here. Well, it's because I've got one of my favoriteest people in the world on the show to help us look at embedded programming, embedded processors, and lights, specifically digitally controlled lights. We welcome back to the show Mark Smith, Smitty Halibut. Smitty, thanks for coming back on the Coding 101.
Thanks for having me.
If you don't mind, I'm going to actually de-power glove here for a second here. This is something we actually created for Know-How. This is a super simple circuit. This is just a electronic speed control hooked up to a PWM switch, which allows me to dim or brighten a strip of 12-volt LEDs. But these are not programmable. These are all dumb LEDs. You provide power to them and they light up. We're going to be playing with a different kind of beast today, aren't we, Smitty?
We are. We're going to be playing with individually addressable RGB LEDs, where you can send them as a single data pin that goes and will address the entire string, and you can tell each individual LED what intensity for each of the red, green, and blue colors, and therefore you can make them pretty much any color you want them.
Right. Let's actually start with that because people are going to be a little bit confused. We're going to be playing with WS2812 and 2812B LEDs. These are interesting devices. Actually, Anthony, if you go to the overhead, you're going to see the WS2812s here. These don't look a whole lot different than the ones that are encapsulated inside that weatherproof strip. But the difference between these two is that the WS2812 actually has an IC. There's an integrated circuit there that allows me to individually control every single LED inside of a strand, versus this, which is these are all connected to the same common voltage rails. So if I provide voltage to one, I'm going to provide voltage to all. Now, Smitty, what's the practical use of something like this?
Well, it means that you can do kind of cool animations. I don't know if you can see it with the backlight on here, but here's an example of a bar of 8 LEDs that I have. That's just kind of, this is a program that my daughter wanted me to write up. It's just kind of a rainbow that cycles through. You can kind of see it's green at the top, then now it's blue and went up to red. And so the rainbow is just kind of falling down the row of LEDs there. And you can set individual colors on any of them. You can use them to do animations, do artwork, do little projects, or in my case, you can do some very functional things with them. I have, hey, it powers off on this one. Trust me, this is a clock, and it looks really cool when it's powered up, and I'll get it powered up in a second.
Right. The very cool thing about this is because they're all connected serially, there's no complicated wiring. As long as you can connect the digital pin on one LED to the digital pin on the next, you'll be able to control each and every single one of them in an array, assuming that you know what position in that strand that LED is. Okay, Smitty, correct me if I'm wrong, but I understand the way that WS2812 works. Let's say I have something like this. This is a pixel stick. I actually purchased this from Ready to Fly Quads. So it's 8 WS2812 LEDs in a series. I would create an array of 8 values, and those values would include the color and the brightness. And then I would use my controller, in this case I'm using an Arduino, to push that array through the stick. And every single LED that receives that signal, it takes the one that it gets and then it passes on the rest. And so you can go down the entire line, assuming you know how big that strand is.
Correct. So the way it works is you have you start sending data. So your microcontroller starts sending out data, and it's 1 byte per color for each of the LEDs. So the first LED says, hey, I've been quiet for a while. There's no data. Data has started. All right, I'm going to take the first byte, and that's going to be my, it's actually green, red, blue, which is kind of annoying. But it takes the first byte and says, that's green. That's the value I'm going to use for green. Then it takes the second byte. That's the value I'm going to use for red. And it takes the third byte, and that's going to be the value it uses for blue. And it consumes those bytes, and it does not send them out. But any data after that, without a pause, any data that comes right after, immediately after it, it will just send out of its data output pin. If you take that data output pin and send it to the next LED, then the next LED says, oh, it was quiet before because it didn't hear those first 3 bytes, but it hears the next 3 bytes, and it will consume those 3 bytes, and anything that comes after it just gets passed down the line. And so the first LED in your string sees all of the data, but it only consumes the first 3 bytes and just passes through everything else. Then the next LED sees everything except the data for the first LED, consumes the next 3, and passes everything else. And so if you've got a string of 8 of these things, you will end up sending 24 bytes down the wire. The first 3 will get consumed by the first LED, the next 3 by the next LED, so on and so forth. And when you get down to the last LED, all it sees are the 3 bytes for it, and that's it. It doesn't see anything else. Then you have to pause long enough at the end of the whole array so that the first LED says, oh, there's no more data, I'm stopping. Now the next data that I will see, I will start consuming again. And in that way, you can individually address every single LED, but it does mean that you need to output data for every single LED on the chain every time you try to update it.
And it also means that you have to control the timing of the signals. They can't just be constant because, as you said, there has to be that pause. It has to know, okay, this is a new string of data, go ahead and take this. Correct. Which is why you need something like an Arduino, an Atmel chipset that will do that output for you in the proper format. Now, let me ask you this. I've seen another style of individually controllable LEDs that uses a timing line. So you have negative, you have positive, you have the power and the ground, then you have the digital control line, and then you have the timing line. Why not use that rather than this 3-wire setup?
Well, so you say timing line, you mean like an I2C bus,
right,
where you've got the serial data and the serial clock? It's just a different bus. I2C is has some limitations as to the number of devices you can have on the bus. If you have too many devices trying to read the bus at any given time, then you need to have a super powerful transmitter. Whereas this one, every single device on the chain regenerates the signal as it goes through it. So you could have chains that are basically infinitely long, although the longer they are, the more data you have to send down the line and the slower your refresh ends up being because it takes longer to actually update the whole chain. But an I2C one would allow you to update individual pixels without having to update the entire chain.
Right. Smitty, let me ask you this. I know that you're playing with, is that a 60 LED ring that you've got?
This one, yeah.
60. And I've got a couple here. I've got this, which is a 16 LED. It's a ring. And then I've got a bunch of NeoPixels. Now, I can daisy chain these, so I can make them longer and longer and longer. For the people out at home who are salivating right now, they're wondering, well, I want to make one of these on my own. How am I going to do it? What's the practical length that you can do? Because obviously you can't go on forever. How many LEDs can you put in a series before the WS2812 spec says stop?
I'm not sure that the spec has a limit. Where you're going to run into problem is power. You do need to be able to provide power on your +5 volt and your ground line for all of these LEDs. And so if you have them all on full brightness, full white, that's going to consume a fair bit of power. And so you need to be able to power them individually. The other limitation you're going to run into is the when you are the libraries that you use to update these, they consume 3 bytes of memory internally for the buffer. So you say, all right, for this pixel, I want this value. And you tell that to the library, excuse me, at the beginning. And then when you get all your pixels updated, you say, all right, go. and it spits all of it out over the data line into the string. And so you need to be able to have enough memory inside your microcontroller to be able to update those. It seems weird in this day and age to be talking about memory constraints, but my platform of choice, and I'm looking for an example of one, my platform of choice for these things is a DigiSpark, which is
nice.
a very tiny little microcontroller. It's based on the ATtiny 85, and it has 512 bytes of RAM. Not kilobytes, not megabytes,
Bytes.
512 bytes of RAM. And so I need to fit my entire program local variables into that space, including the buffer that the pixel library uses. And so the pixel library stores 3 bytes per LED in its buffer, and then I was storing I had an array of 32-bit values to store the millis value when a twinkle started, and so I was storing a total of 7 bytes per LED in memory, and at 50 LEDs on this string of Christmas lights that I have, ended up being 350 of my 512 bytes just in array buffers to control these things, and the rest of my program ended up taking more than that, and I overflowed my memory, and it wasn't working. So that's one possible limitation. The other limitation is that the longer your string, the more time it takes to send out that serial data all the way across to be able to update the entire thing.
Right.
And so the longer it is, the longer that period, the lower the frequency of updates. So you might end up, if you get super duper long, you might end up with kind of flickery LEDs, as it just takes a while for them to update.
Right. I should mention, if you go on Amazon right now, you're going to find a bunch of different vendors who do 2812 LEDs. Do you have a policy for this? Because I found it to be buyer beware. I've bought 2 spools so far. One were fantastic, and the other, it was a 5-meter length of 144 LEDs. And they were horrible. They flickered. They were very, very inconsistent as far as addressing was concerned. Is there a vendor that you trust more than another, or is there a way to look at vendors and figure out which one is better, other than looking at reviews, which are probably stacked?
No, I don't have any words of wisdom here. I buy my stuff off of eBay. Before the show, I kind of grabbed the camera and showed my storage unit back there, my storage shelf with all of my bulk purchased parts. Most of those are from eBay. I so far have not had bad luck, although now that you mentioned it, I have noticed flicker on some of these. But that's usually because I'm running them off of a USB port off of my computer on an unpowered hub, so it's who knows what the power is like. If I gave it a better 5-volt supply, I might have less flicker on that.
Right. I do want to address that memory issue that you mentioned earlier. If you go to the overhead, this is what I'm doing my project on. This is an Arduino Uno. Now this is a nice machine. It's actually way overkill for 8 LEDs. It's way more memory, way more processing power than I'll need. But I also have this, which is just a simple stick. There's no logic here other than the ICs that control each individually addressable LED. Then there's this. This looks just like another strip of WS2812s, but there is actually an Atmel chipset right there, which is why I've got this USB plugged in. I can program this to control just this set of LEDs. And then I've got something like this, which is larger. It also controls a ring of LEDs, but it's got a bigger, more powerful Atmel chipset, which allows me to control these LEDs plus anything else I might string along. So as Smitty was saying, know the size of your job before you start programming for it. He's trying to fit everything into, what device is that? That's a SparkFun something or other?
It's a DigiSpark.
A DigiSpark?
DigiSpark, yeah.
So he knows how big of a project he can do. If you're planning on controlling 400 of these, you're not going to want to use anything
not a DigiSpark.
No.
And Uno should be able to do around 400 LEDs. That wouldn't be a problem, because that's 400 LEDs. I'm sorry, did you say 400? Yeah, 400 times 3.
I had 300 powered up last night, and it was not a problem. It was
not a problem,
easy.
yeah.
Now, folks, when we come back, we're going to take you into the code. We have these, and these are ready, and they are here, so you'll be able to download them as soon as the show is done. But if you have an Arduino, if you have some WS2812 devices in your room, in your lab, you will be able to start playing with lights immediately. But before we do that, let's go ahead and thank the first sponsor of this episode of Coding 101, and it's lynda.com. Now, if you've watched Twit TV, you know what lynda.com is. It is our preferred repository of knowledge on the internet. And it's not just for programming knowledge. It's not just for hobby knowledge, photography. It's not just for things like business skills and Excel. You could do that. But you could also use lynda.com for self-improvement, for management skills, essentially to improve yourself. Lynda.com is for the makers, for the doers, for the creators, for the curious, for the people who want to get it done. I've been excited by some of the courses that lynda.com has been adding over the past couple of weeks. They include an introduction to data analysis with Python, Cake PHP 2 Essential Training, Xcode 7 Essential Training, and Link with C# Essential Training. They've also recently updated their Beginner's PHP course, Introducing PHP. Whether you're a beginner looking to learn your first language or an expert learning to master a new one, lynda.com has something for every level of experience. Once you get a lynda.com experience, you can watch and learn from top experts, people who are passionate about their work, about their hobby, about the skills that they're trying to give you. That's really what you want. You don't have to worry about production values, bad lighting, or bad audio. Lynda.com takes care of all of that. Instead, you can focus on the person, the man, the woman, the expert who wants you to learn what they know. You can also learn on your own pace. You can create playlists and save them for later. You can download them to your iOS or your Android devices. My personal favorite is the fact that they've got transcript for all their courses. So you can look for a specific passage, a specific problem, a specific solution, and jump to it inside of the video rather than watching an entire segment, an entire library of courses. You can take notes as you go and refer to them later. You could also share your courses with your friends so they know what you're passionate about right now. This is sort of social for the people who want to learn. Folks, we use lynda.com because it is undoubtedly the best place for knowledge on the interwebs. We think you should use it too. Now, your lynda.com membership gives you unlimited access to training on hundreds of topics, all for one low flat rate. Whether you're looking to become an expert, you're passionate about a hobby, or you just want to learn something new, I want you to visit lynda.com/C101 and sign up for your free 10-day trial. That's lynda.com, lynda.com/C101. And we thank lynda.com for their support of Coding 101. Let's jump into it. For those folks who want to play along at home, here is the little project board that I've got. Go ahead and give me a shot there. So don't mind this. This was me being bored and wanting to print up a little 3D printed project case. This is a breadboard. I don't need that. I could wire this entire circuit just hardwired, hard solder. But I did want a little bit of flexibility so I can play with this because, of course, last night I wasn't doing 8 LEDs. I was doing 300. Now, this is an Arduino Uno, so you can get one of these. Actually, this is the clone that you bought me the last time you were on Coding 101 with a project. Do you remember this?
I do.
This came from our little panel meter analog clock. This is just a breadboard, standard breadboard. I think I got this for about like 1068, including all of the jumper leads. The Arduino clone was about $10, and then this WS2812 LED stick I got from Ready to Fly Quads for $325. So I bought a bunch of these. This is actually even cheaper than when you can get it on SparkFun or Adafruit for. And I actually like these more because I'm not sure if you can see. Can you see on this side here? They've got these little sockets so that I can daisy chain these without having to solder. So if I just want to test out an array really quickly, I just link these together with a quick jumper. Again, there's just 3 leads. There's positive, there's negative, and there's the digital output. So the way that this works is I've got 3 lines coming out of my pixel stick. Black is providing ground, red is providing 5-volt power. This green is really the important one. So this is providing the digital logic. That's the signal that Smitty was talking about. When it's passing down the bytes down the strand, it's going to come over that green line. Now, it's hooked up to a potentiometer, and the reason why it's hooked up to a potentiometer, I'm going to show you really quickly. Let me go ahead and give power to this. As soon as I stopped knocking out the leads. I tried to clean this up last night, and as it turned out, I just ended up making it kind of a pain in the butt. So I'm pulling some pins from my Arduino. I'm pulling this, which is digital pin 7. So digital pin 7 is driving the logic on my WS2812 LEDs. That's where the logic is coming from. I've also got pull-ups over here. I'm taking power. This is powered straight off of the Arduino. There is no other power other than the USB that's coming into my Arduino Uno. Now, I will say this. It works fine if you're going to do, I'd say, up to three strands of 8. Anything more, you're going to want to use an external power supply. I think the Arduino Uno can, if it's running off of USB, it can provide 500 milliamps of power. each of these LEDs can pull up to 60 milliamps because it's 20 per color. So do the math. If you're going to be going too high, go ahead and give it an external 5-volt power source because you don't want to overtax your Uno.
Are you pulling power from the 5-volt source or from the VN source?
I'm pulling it from the 5-volt source.
Okay, so you're running through an additional regulator, which might be a problem. If you pulled it from VN, you would be pulling straight from the USB.
Right.
And that would probably give you a little bit more power.
Yeah. I'm going to be playing with this because I want to make this portable. So there's another layer that goes underneath this project board that will provide all the power I need. Because ultimately, I want to make this something I wear on my wrist, like I did with that other one. But that's a know-how project. We're not going to talk about that now. Then I do one more.
That's another show.
That's another show. This one right here, this is actually an analog pin. So I am pulling from analog pin 1. The reason why I'm pushing into analog pin 1 is because I want to give it an analog value, which is what this potentiometer does. It's going to give me between 0 and 5 volts, and as I increase the voltage, it's going to increase the value of that analog pin. So let me show you what the practical effect is. If I go all the way down, actually drop the lights, let's see. There we go. If I go all the way down, I already have these set at like, I think, 30% brightness. It's going to give me a couple of yellow LEDs and 2 pink LEDs. As I come up, it's first going to blank out, and then as I increase, it's going to slowly increase from blue to green to orange to red. And finally, when I get up to the top of the range, it's just going to go into a little Christmas mode. Now, we're going to show you exactly how that works. But as you can see, this circuit is crazy, crazy simple. This is something I did in about 10 minutes, and then the rest of it was just coding. Speaking of the just coding, let's go ahead and show you what we've got. If you go ahead and jump over to my input 11. So there are 5 basic pieces that we're going to be using for the library that I have chosen to use. I'm using the FastLED. It's a library that you can download off the internet. Smitty actually gave us a really quick tutorial on how to add libraries to your Arduino IDE. There is a folder inside your Arduino IDE that says library. Just whatever you download after you've unzipped it, drop it in there, and it will be included. There will be a library that you can pull from. So
actually, the newer versions of Arduino have made it a heck of a lot easier. If the library writer makes a specific format of the URL, there's actually a library manager in the newer versions of the Arduino IDE that makes this a heck of a lot easier.
Oh, so will it auto-fetch libraries already? So like if I just put FastH, will it know to look for it?
No, it doesn't know where to look for it. You need to know a URL where the FastLED library is, but then you can program it into the library manager, or you put it in the preferences field, and it will just download all the libraries. And I think it keeps them up to date and everything. It's really cool.
Very, very cool. But I'm doing a super simple one on this because we're leaving the nice, complicated, beautiful one for Smitty. Let's take a look at the code. So I need 5 pieces to make use of the FastLED library. The first is an include. This just tells my IDE what library it's going to be pulling from. It's going to be pulling from the FastLED library. The second thing is this, define num_LEDs. This is where you tell the library how many LEDs, how many WS2812s I have in my array. I only have a stick of 8, but last night when I was testing it with 300, obviously I put 300. The reason why it's important for it to know that is because it's going to be sending out an array, and it's going to be dividing up the number of bytes it has to send up based on the number of LEDs you have. It needs to know how many LEDs are in the array. We're going to see why that's important in just a bit. The third piece is this. Remember I told you that I was using data pin 7 to control my WS2812s. So I have to define the data pin. Actually, we did this when Smitty was doing the Arduino clock. Number 4 is this, CRGB LEDs num LEDs. What I've just done is I've created an array called LEDs, the length of num LEDs, which I defined above. So I just created an 8-element array. And we're going to show you why that's important, but that is actually very important. The last piece, the last basic piece that you're going to need is this. Inside the setup, your setup here, void setup, you need to have FastLED, add LEDs, and then this gives it the library it's going to be using, the data pin it's going to be using, the number of LEDs, and where it's going to find that array. Now,
have you covered C++ templates on Coding 101?
Not on Coding 101, no. Well, actually,
okay.
we might have. I don't know. I'd have to look back. Oh, this line here, this is not necessary. This is a debugging line. All I did was I asked for a value to be pushed. I had to open up a serial console because, well, you're going to see later, I want to be able to show you what the analog values look like. Okay, so that has me set up. Now let's look at what the actual program loop looks like. Now, Smitty, I made this short, but I bet you could make it shorter. Remember how we said you want to, in the main program loop, you actually want as little code as possible. That was one of the things that we agreed upon, yes?
Sure. I'm chuckling because wait till we get to my code. Yeah, go on.
The original version of this that I made, I was super lazy, and I put everything in one loop. As a lot of programmers do. And then I got okay, I have to fix this. So I went back and I started chopping everything out. Now, if you look at this, so this is the logic for the entire program. It starts by initializing a variable. It's an integer called aread, and it's analog read 1. So it's saying create a variable called aread and put into that variable the value that you're getting off of analog pin number 1. That's the read. And then this line, again, I don't need this. This is a debug line. This pushes that out to the serial console so I can actually read what that value is. Now we start with the if-else statements. There's 3 of them, if-else, and an else statement. If that variable, so that value that I just pulled from the analog pin is greater than or equal to 0, but less than 50, then I will call the function WS2812 low. If that value, again from that analog pin, is equal to or greater than 50, but less than 1000, then it will call the function WS2812 mid. That's the mid-range. Else, and this covers everything else, so if it's not low, if it's not mid, call WS2812 high. What I've just done is I've given myself 3 different outcomes depending if that range coming off of the analog pin is low, mid-range, or high. Smitty, could I have made that smaller, or is that okay? I mean, I'm gonna defer to your judgment here. Did I do okay by eliminating things from the main loop?
Yeah, you did a fine job. Unfortunately, with the Skype, it kind of chops off the side, so I'm missing the first bit of your code on the side. But I remember looking at it. Yeah, your main loop doesn't have to be empty. You don't want to put the bulk of your logic in there. And I am totally being hypocritical when I say that, because when we look at my code, it's almost entirely inside my main loop. But no, yeah, yeah, I mean, putting like the high level logic in your loop function is fine.
All right. Now the Arduino is already loaded up, so it is reading. So what I'm going to do is I'm going to go ahead and open up a serial console, serial monitor, so you can see what's going on inside of this thing. Let's see if it's still, there we go. So that analog, that's the value. So anytime I do a read from an analog pin, I'm going to be getting a value of 1024. That's 10 bits between 0 and 1023. So let's do the math. Each value is separated by 0.0047 volts. The pin is going to sample 10,000 times each second. I've actually put a delay because I don't want this thing just scrolling like crazy. I put a delay of 200. Now, if you go ahead and look at this, as I increase and decrease this, you're going to notice those values go up and down. So these are the values that are going to determine what the Arduino is going to be doing to the WS2812s. Now, Smitty, I know I've had questions, I've had concerned tweets from people. If you go back to the monitor screen, I've got the potentiometer all the way down, and people go, how come it doesn't stay at 0? You see it jumping 3, 13, 11, 4, et cetera, wait, there we go.
It's over there somewhere.
Right. And why does it do that? I mean, we're going to find that anytime we're using an analog line.
Yeah, so it's not perfect. I mean, potentiometers, even when you turn them all the way down, they still have at least a little bit of resistance there. And when you have a little bit of resistance, you're going to get a little bit of a voltage drop. And even if you were to just tie your analog read to ground, those transistors still don't go quite full rail to rail. So they will always measure just at least a little bit. I don't think you'll ever be able to get an analog pin all the way down to 0 reliably without actually taking it to a negative voltage.
Right. And I only bring that up because this works because I've only got 3 triggers. So I've got a low, a mid, and a high trigger. But if you think you're going to get 1,024 discrete levels that you can count on to stay there.
Yeah, no kidding.
No, it's not going to happen.
So for us,
I give about 50.
Old people,
I say 50 is my rule.
You remember for us old guys, you remember the old days when we used to have a joystick hooked up to our computer and we'd have to calibrate it by bringing it around. And the reason we did that is so that the computer could actually measure where the maximums and minimums of your analog reads were.
Precisely.
Yeah.
All right, now let's go ahead and look at what the actual functions do. Let's take a look at low first, because low is the easiest one. I specifically made this ridiculously easy so that you can see what needs to happen in order for your WS2812s to be controlled. Actually, that's high. Let's go low. There it is. There's low. So here we have WS2812 low. So this is it's a function of its own. There's no parameters. I don't have to pass anything to it. It's just when it gets called, it does this. What it's doing is, remember that LED array that I created. It's going from 0 to 7, so 8 elements, and it's filling it with the value CRGB yellow. And all that means is it's going to try to put yellow into that array. Below it, I've got this, FastLED set brightness to 30. That goes from 0 to 100. So this is at 30% brightness. And then FastLED show. FastLED show in this library will push the array down the line. This is what Smitty was talking about. So I've now got those bytes stacked up containing the color that I want and the brightness. I'm now pushing it down the line, and every LED will take its bytes and pass on the remaining to every other WS2812 device down the line. It's that simple. Create the array, push the array down the strand. Am I missing anything there, Smitty?
No. You do something that I actually don't do in my code. You have a set brightness, which I think is just a scaling factor that the library adds to the values. I actually do the scaling on my own before I set the color, and I leave the library scaled to full brightness.
Right. And I actually have it at 30, because if I have it at 100, it would actually blot out the camera. These are actually really, really bright LEDs. Just
yes, they are.
Yeah. All right, so that's low. Low is the simplest. Now, I will say this. There's going to be some of you who will look at it and say, why did he manually set the value for each cell in that array? And I didn't have to. Smitty and I are both doing this. Our code is far from being optimized. We would like to see you take it home and optimize it. Like, for example, there's no reason why I can't fill this array with a little loop. So that's a challenge to you. All right, let's go ahead and look at the second one. So I've got my low. Let's look at mid. Mid is the complicated one, because if you go ahead and go back to the overhead here, you'll notice when I'm at low, it's simple. It's just, actually take the lights on again. There we go. I've got just a solid line of lights. As soon as I hit mid, what's going to happen is, as I increase the potentiometer, I'm going to slowly get more and more lights. So obviously there's a bit more logic here than just fill an array and push it to the stick. I have to make it do something, and that's what we're going to show you now. So let's look at the logic of WS2812 mid. Now notice the first thing is I passed it something. This passes the value from the potentiometer. I didn't need it for low, because low was just, I just needed to trigger it. I didn't have to give it any values. But this, I do need what the value of that potentiometer is, because I'm basing what the function does on where that potentiometer is located in its range. Let's look at what's inside of here. First, this int, so I'm creating an integer, light map equals. This is an interesting function. I actually only started playing with this about a month ago. I really, really like it. This is really, really nice for people who are going to be playing with Arduinos. Position mapping. So I already know that I have a range of 0 to 1023. So that's 1024 potential values for my analog read. This maps that value onto the number of LEDs I have. So I don't have to do any math. I don't have to say, okay, for 0 to 50, it's LED 1, and then 51 to 100, it's LED 2. This takes the range that I gave it, because I told it how many LEDs I had, and it maps it on top of the range that's possible for the analog pin. This saves me a lot of work. Smitty, I actually did this manually the first time, because I had no idea this function existed.
I've never seen that function. Is that a part of the FastLED library?
That's part of the FastLED library. It's really nice. I love this. It saves you so much time, and it also means, this is the important part, when I switched from using just 8 LEDs to using 300 LEDs, it did the mapping for me. I didn't have to redo the math. Yeah, super sweet. Really like that. All right, now this is important. FastLED clear. You could actually not do this, but any programmer will know that you want to. You want to clear out the array, because if you don't clear the FastLED string, what's going to happen is you may actually have a couple of values that get left over. And if you're trying to do any sort of animation, that's bad juju. All right, now I've got a loop. And this loop it's not terribly complicated. It's going to tell me for LED 0 all the way up to the range, which I determined up above in light map. If I'm at the range of 2 LEDs, it's going to light up those first 2 blue. It's going to light up the next 2 green. It's going to light up the next 2 orange, and it's going to light up the next 2 red. Now, the wonderful thing about this is I can make those values anything. And I can actually create more divisions here. If I had a 300 LED string, I could have a ton of divisions. I could divide it by 8, divide it by 16. And this part, I haven't figured out how to remap automatically, so I do have to adjust that if I do add LEDs. So right now it's only set up to go to 6, but I'm pretty sure I should be able to use the position function at some point in the near future to automatically do this. In fact, folks, I think you should be using the position function. So again, that's something else that you can clean up. After that, basic. Set the brightness. In this case, I'm setting it to 60, and then show. So push it down the line. Let's look at the third one. This is if I go all the way, 100%. Now, this is kind of weird because I fill 2 arrays. And you'll notice that I'm not using blue, yellow. I'm actually using a hexadecimal representation of a color. Anyone who's done any sort of web development knows what these are. These are just values. These are color values, so I can get an exact color that I want. I'm filling the array with that color. I'm setting the brightness, and then I push it down the line. And then I fill the array again with another set of values, which is actually an alternating set of values, and I push it down the line. And that's when I get, if you go to the overhead, that's when I get this. So when it's animated like that, all it is it's 2 arrays that are going back and forth, back and forth, back and forth, back and forth, back and forth. I set a delay of 200, but if I wanted it to go more quickly, I'd set it for a shorter delay. If I wanted to go more slowly, I would set a longer delay. And that's it. That's all the code that's in here. Now, the wonderful thing about the FastLED library is it is incredibly complicated. There are so many functions in there, including the ones that make it do things like this. So it's the exact same library, the same library that I'm using to do these super simple animations and these super simple little lighting effects I can use here to make sort of rainbow color. And there's a function called rainbow, which will do something like this. So what I would recommend is go ahead and download the IDE for Arduino. Get yourself probably an Uno, because you're going to want a little bit of stretching room for when you grow beyond your projects. Get yourself a couple of WS2812 LEDs, and we're going to have links in the show notes so you can buy them right away if you want, and then just start experimenting. Now, Smitty, we did this first because this is super simple. You did something I really like. It's actually quite beautiful. We're going to get to that in a bit, but before we do that, let's go ahead and thank the second sponsor of this episode of Coding 101. Now, let me ask you something. Do you develop? Because if you do, at some point, you're going to need to get paid. I mean, it's nice to release things out into the wild, release them out into the world, but if you don't monetize, if you don't have a way to keep it self-reliant, well, it's going to crumble. Now, the old way to do that was to create some sort of server, financial transaction server. Maybe get some sort of an arrangement with a financial processor so that they could take credit card receipts. And of course, you have to maintain everything, because if you, God forbid, you ever lose your customer's financial information, you're done for. Well, you could worry about all that, but that is so 20 years ago, because today, we've got Braintree. Braintree is the easiest way to add payments to your app. And by payments, I mean anything. Android Pay, Apple Pay, Bitcoin, Venmo, credit cards. You want to take currency from around the world? You can do that. Braintree gives you all of that in a simple 10-line integration. Now, what I really like about Braintree is the fact that they've got this thing called a sandbox. And the sandbox allows you to test an integration with real-world seeming traffic without actually having to risk your infrastructure, your programming, your financial transaction information on the internet. Now, this is all done with the Braintree V.0 SDK. And the Braintree V.0 SDK comes in 7 different languages, from .NET to Node.js, Java, Perl, PHP, Python, and Ruby. The code itself supports Android, iOS, and JavaScript clients. And they use tokens, which means that the important information, the sensitive information, is never exposed. Folks, this is the way you want to receive payments on the internet. Now, if you are ready ready to try the most secure, the easiest integration, the best vendor we've ever seen for mobile payments, I urge you to try out Braintree. Braintree gives you that easy way to accept the payments that your customers want, and they make it simple enough that you can do it on a weekend. Try out the sandbox for yourself at braintreepayments.com/coding. That's braintreepayments.com/coding. And we thank Braintree for their support of Coding 101. Well, Smitty, I think we're done with grammar school here. So we're going to have the links and the instructions for them to do this. Let's show them what the college kids have come up with.
Yeah, don't sell yourself short, man. There was some good logic in there, some good good decision making, and some neat way of doing some animation and stuff. You got some good stuff in there. I was impressed.
Yeah, but I want to see.
Mine doesn't have any input.
I want to see this nice all 60 LED ring because that thing is beautiful.
So this is a 60 LED ring that I got off of eBay, and I think Adafruit has one as well. And so it's actually this program that I'm running on there right now started with some Christmas lights like things that I also got off of eBay. These are just a string of 50 Christmas lights that are the WS2812 chips in there and multicolor LEDs. It's not hooked up right now, but when I was a kid, I was always responsible for putting the lights on our Christmas tree. And I hated the fact that we only had the Christmas lights where you put the one bulb at the beginning or the end of the chain and it would blink the entire string all at once, right? And I hated that because it looked chunky, right? It didn't look nice and twinkly and pretty, right? And so I always had this dream of being able to twinkle each individual light randomly. And I didn't want them like alternating and doing these patterns or anything like that. I just wanted individual lights to twinkle randomly. And so when I saw these Christmas lights that were the 2812s, I decided to buy some. And these were less than $20 on eBay. It's a string of 50 of them, and it's I never actually measured it, but it's a nice little string of Christmas lights.
Are those 5 volt or 12 volt?
5 volt.
Oh, nice.
They're 2812s, just like all the other ones. And so I wrote this program. I'm just showing you on the ring because it's a little easier to show it, but I wrote a program that twinkles each individual light individually, and I can modify this program so that instead of the default state being off and then they twinkle on, I can make it so that the default state is on and that they twinkle off. That's another way of doing it. The color might be a little bit washed out, but you can also tell that most of them twinkle white, but occasionally you'll get a red or a green or a blue in there as well. So there are, lots of different programs that you could do, but the idea behind this program is that it will be kind of a nice random twinkly Christmas tree is what I always wanted as a kid. And now that I'm 40 years old, I can make it happen myself.
This is one of the things I love about the WS2812s. This is what makes them so flexible. You've got them in Christmas lights. I've got them in these pixel sticks. And you've got them in a ring, but they're all the same. They're just hooked up serially.
Exact
you connect power, you connect the digital out to the digital in, and you're good to go. And you can go as many or as few LEDs as you want.
Yeah. Literally, I'm just running this onto the ring because it's easier to show in a webcam. I can unplug the ring and plug in the Christmas lights, and the exact same program works beautifully on both of them. All
right. Now, do we want to show them the nitty-gritty?
Sure, let's do it.
All right, so go ahead and go to my screen. This is now Smitty's code. And again, this is already in our Dropbox. So assuming our editor doesn't just ignore the notes, Kevin, please don't ignore the notes. He's going to give you links for this as soon as it goes up. So you'll be able to download our code. Don't feel the need to copy it off the screen. All right, so where am I starting?
Oh, let's go start at the beginning. So one of the things that I've started doing recently is I put a little comment up there that say, these are where you edit your configuration values, because I have some other pound defines that are not configuration values that I don't want people tweaking with. So if you're going to download this code and you need to modify it to work on your own hardware, keep your modifications inside this configuration zone unless you want to start hacking things.
Right. I'll notice that I use the FastLED library. You're using the Adafruit NeoPixel library. They can both address WS2812. So just choose the one that has the functions you want to play with.
Correct. Honestly, I used Adafruit because it was the first one I found. I didn't even know about the FastLED. If I'd known about it, I would have tried it.
Yeah, I love it.
But Adafruit's doing just fine for me, so that's the one I'm using. Again, just like yours, we have to do the pound define of pixel pin so we know which pin the LEDs are connected to, what the data out pin of our controller is, and then that will go to the first data in on the first LED.
Smitty, really quickly, some of the digital pins can do PWM, right? So I remember you telling me you prefer not to use the PWM pins if you don't have to, just because you want to reserve those for later.
True. If I'm going to be doing something where that needs PWM, correct.
Right. And is that 1 through 3, or I can't? I forget.
Oh no, it's random. It's random. It's arbitrary. I've got a Arduino around here somewhere. They're usually labeled. They're the ones with the little tildes next to the numbers.
Yeah. And if you are wondering what PWM is, actually look at the last Coding 101 module that Smitty did, because he explains it quite well while he's making the clock. We also did a know-how episode on how PWM works, but we're not going to do it right now.
I think that was episode 41 or 43.
Yeah. Actually, wow, about a year ago. Not bad.
Yeah, crazy.
All right, so I've got my digital pin that's going to control my my logic. What's this next one?
To be clear about that, though, we do not need PWM for this. It is doing all of the logic in software, so we do not need pulse width modulation. The next one, num pixels. Gee, I wonder what that is. That is the number of pixels in our ring. And I'm realizing now that I have mine programmed for 50, so the last 10 LEDs of my ring is not actually ever going to get lit.
Actually, no, that was on purpose. So if you've got a ring, folks, how do you make it address all 60?
Sure, yeah. We're going to make people fix my code. There we go. That's a good idea.
I like that.
The next one is the ramp max. So we do a lot of ramping up and down of values on while we're twinkling. And so I want to know what the maximum value of that ramp is going to be. I could make that 255, but I made it 200 so that it's a little bit less bright than full brightness. And honestly, once you get above 200, it's hard to tell the difference between 200 and 255. So you might as well stop it when you get to the top of your observable maximum, and you save a little bit of power.
Right, exactly.
So the next one, twinkle every. That is a value that we are going to take a random number between 0 and that number. And if that random number is 0, then we will do, we'll set a green LED or a red LED or whatever. If it's 1, we'll set a green LED. If it's a 2, we'll set a blue LED. If it's between 3 and 9, it will set a white LED. So it's basically we're just going to take a random number between 1 and 10,000, and, for a few of those values, we will start twinkling. If you want to make them twinkle more, then you decrease this number. If you want to make them twinkle less, then you increase this number.
Got it. And that's milliseconds?
No, the 10,000 is just a chance.
Oh, okay. Got it.
Because we are using values 0 through 9 later on, you have a 10 in 10,000 or a 1 in 1,000 chance of deciding to start to twinkle. And you make that decision individually for every LED 50 times a second.
So if I put it in 10 and 10, it just stays lit.
They'll all stay lit.
It's all twinkling. Okay, got it.
Exactly. And then the next one is the loop every. And so basically you had a delay in your loop of a certain number of milliseconds. That's what this is. So we're going to loop every 20 milliseconds. And 20 millisecond loop gives you a 50 hertz refresh rate.
Got it. Okay.
And then milliseconds to ramp up and milliseconds to ramp down. So that gives you the ability to kind of shape your waveform, your twinkle form, right? So I'm going to ramp up over 500 milliseconds, and I'm going to ramp down over 1,000 milliseconds. So it'll twinkle up quickly and then kind of twinkle down a little little slower.
Right. Okay. So that's your configuration. That tells it how many LEDs you have. Tells you how often you want to twinkle, and it tells you the range for ramping up and ramping down, after, of course, telling it that you want to use the Adafruit NeoPixel library. Now that you've got all that set up, what else do we have?
So the next down, I've got some other pound defines here, which is just basically a way of doing math at compile time. There's no reason to do this math at runtime, because it doesn't change. We're doing math on our pound defines, so I'm just going to go ahead and do them in pound defines as well. And it does it once, and then it stores the result of that value in the code that gets loaded onto the chip. So ramp up increment. So the way we're doing this is every 20 milliseconds, we are going to add a certain amount to our colors. And this is just a calculation of how much we need to add to our color. So the ramp max is, remember, the maximum value that we want to end up at. The loop every is how many milliseconds is every loop. And then the ramp up is over how much time, how many milliseconds. So what we're actually trying to do is I'm trying to do ramp max times loop every over ramp up. So loop every is 20 milliseconds. So every time we go through this loop is 20 milliseconds, but we want to ramp up over 500 milliseconds. So 20 over 500 would give me, what is that, 25? Is that math right? 5 into 100, 500, yeah, 25 times. So that'll give me 1 over 25. So you basically want 1/25th of your ramp max to be added every time you go through the loop. One thing to note, we are doing integer math here. You do not want to just say ramp max times and then a small number over a big number, because if you do the small number over a big number, that will equal like a fractional number. And since we're doing integer math, that fractional number becomes 0.
Don't do that.
Right? So you want to do all your multiplies. So you want to take all your numerators, multiply them together, then divide, parentheses, all your denominators multiplied together, close parentheses. And that will make sure that you're doing your integer math without actually losing your rounding numbers. You want to go up before you go down when doing all your calculations.
All right. Good.
Anyway, so we're figuring out what our ramp up increments are going to be and our ramp down increments. The next thing down is a way of masking out, because we're using 32-bit numbers to represent colors. And as we're passing them around from function to function, we're actually only using the first 3 bytes of them. But the lowest byte is the blue value. Then the second byte is the green value, and the third byte is the red value. And so what this is doing is, if you give it a 32-bit value for the full-on color, it will take out each of those individual bytes and bring them down into a value between 0 and 255.
Got it.
So actually, have you ever done pound defines with functions? I'm pointing at my own screen.
Actually,
you guys
no,
can't see it.
I have not. I didn't know you could do that. But now I'm looking at this going, that's actually kind of cool.
So if you do parentheses X and close parentheses, and it doesn't have to be X, you can do multiple values there, like X, Y, or RGB or whatever. But if you have a value inside parentheses, then it will substitute that in your pound define. And so, yeah, it's kind of a neat way of it's a C version of doing like an inline function.
Got it. Okay.
Yeah. And then the up-down flag. So this is an interesting thing that I did. Originally, when I did this, I tried keeping track of what the millis value is. Millis is just a monotomically incrementing, I guess that's not a right term, but anyway, it's the number of milliseconds that the Arduino has been powered on. And it's a 32-bit number, so it'll calculate, it'll count up to like 4 billion milliseconds, and I don't know how long that is, but it's a long time. And it just keeps counting up and up and up and up from as soon as the thing resets. And I originally wrote this code trying to figure out where we were in a ramp up or a ramp down of the twinkle by comparing the millis value of when we decided to start a twinkle. And that's 4 bytes per LED, plus the 3 bytes that the NeoPixel library was reserving per LED. What ended up being 7 bytes per LED that we had to store in libraries just to remember state for these things, and that ended up being more RAM than my DigiSpark had. And so I was trying to think of another way. I need some way of knowing whether I'm in a ramp up on a value or whether I'm on a ramp down on a particular LED. And so I decided to use the least significant bit, the 1 bit of that value between 0 and 255 to determine whether we're ramping up or ramping down.
How much memory does that save you?
Say again?
How much memory does that save you?
4 bytes per LED, and if I'm on a string of 50 LEDs, that's 200 bytes.
Okay, yeah, that'll do it. Nice.
Yeah, that'll do it.
Yeah.
So I'm using the least significant bit. If the color value is odd, then that means that we're ramping up. If the color value is even, then we're ramping back down.
Got it. Okay.
And so
actually, that's
anyway,
a very cool little trick there. I'm going to do that the next time I start running out of memory.
So so the up-down flag is just a pound define so that we know which bit we're using as that flag. So I'm just taking a bit out of the color and using it as a flag as to whether we're ramping up or down.
All right. Okay, so now we've got your setup here, and you're calling something inside the Adafruit library, I'm assuming. Begin, clear, and show.
Before we get there, I want to take a look at the line. It's 44 on mine. I think it's the same line that you have it on. We are actually defining our pixels object. right? So pixels is the C++ object that we are using to keep track of the current state and control our LEDs. And so like earlier, you had to define an array and then you had to initialize it. We are actually, the Adafruit library works a little bit differently. It keeps the array inside the object. So it's a little bit more object-oriented in that way. So pixels is the name of our object that is controlling our LEDs. And we give it the num pixels. We tell it how many LEDs we have. We tell it what pin it's on. And then the Neo GRB and the Neo kilohertz 800 is some configuration values, because there are some different hardware types that you can use for these. But that's the hardware type that we're using here.
Cool. All right.
So we're going to be operating on pixels an awful lot.
Yes, we are.
All right. In the setup, we need to do pixels.begin, which tells the pixels library, hey, start doing what you're doing, get things set up and ready for us. .clear just says set everything to zeros. Just make it all dark. And then show says, all right, now we've got an array full of zeros, shove it down the wire toward the LEDs, and that just turns off the current state of all the LEDs. So we have a kind of known starting state for all of our LEDs. Okay. And that's it. Pretty simple for a setup.
All right, so now we go into the main loop.
Into the main loop. So so there's that millis function I was talking about. We save the current value of milliseconds, as in how many milliseconds has it been since we came out of reset, right? And we're going to save that into a variable called now. Then we're going to loop. There's a for loop over all of the pixels, the number of pixels that we have, right? And for each and every one of those pixels, I am going to get the current value of that pixels. So here is where I am using the existing array inside the pixels library, and I'm pulling the state out of it, and I'm going to do some things based on that state. If that, and so I'm saying give me the color of the current LED, and I'm storing that into a variable called color. If that color is 0, meaning that the pixel is currently dark and not doing anything, then I'm going to make a decision as to whether I want to start twinkling. All right, so I'm going to take a random number between 0 and twinkle every, and this is where that 10,000 value came in.
Right. I'm
going to take a random value between 0 and twinkle every. And have you guys covered switch and case statements?
We have, yes.
Okay, so your viewers should know how switch and case works. If that value is 0, then I'm going to decide to start a red twinkle. And I start that red twinkle by setting the up-down flag, which is just the least significant bit in the red color on this particular LED. If it's a 1, if that random value is a 1, then I'm going to set the green up-down flag. If it's a 2, I'm going to set the blue up-down flag. So I've got a 1 in 10,000 chance of starting a red twinkle, a 1 in 10,000 chance of starting a green twinkle, and a 1 in 10,000 chance of starting a blue twinkle.
And then everything else will do a white twinkle.
Well,
between 3 to 9.
3 and 9, yes. So I have 7 times math. Yes, 7 times. I am 7 times as likely to start a white twinkle as I am one of the 3 colored twinkles.
Got it. Okay. Wow. Right. I like that. Simple math.
And so I want to point out there the 3.9. That is.
I have not seen that before. Is that
neither had I? Neither had I. And I did a Google search for, like, is there a way I can specify a range in a case statement? And I came across, I think it was a superuser.com. And I saw an article, and they were talking about this 3.9 thing as a non-C++ standard that has been adopted by many compilers over the last 10 years or so. And it's a way of specifying a range in a case statement. And I didn't know that it existed.
I got to try
that. I saw that. I'm like, I wonder if Arduino does this. And I tried it, and sure enough, because Arduino just uses GCC.
Right. I would have just done a bunch of cases.
That's how I did it in the beginning. Cool. And I'm like, this is ugly. There's got to be a better way to do this. And I looked it up, and there it is.
All right. So that gives us our twinkle based on that random number that you generated, and based on the odds that you set up above on which color it might twinkle to. And,
correct.
Yeah. Nice. Okay. So we've got that.
So that is how we decide if color is 0. If this current pixel is dark, then we are going to decide whether we want to start a twinkle on it randomly.
Right.
Then even if it's not 0, or if it wasn't 0, we're outside of the if statement now when we're on the color equals pixels colors with the ink red. No, up a couple of lines.
Got it.
Yes, that one. So now we're going to increment the colors. And we are going to call out to it. This is the one function that I have outside of my loop. Ink color is a function that I define that we'll go over in a little bit. And here's where we use the red mask, the green mask, and the blue mask. So I am taking the color, which is a 32-bit value, and I'm pulling out the 8-bit value that references either the red, the green, or the blue value. I am passing it to my ink color function, which we will see below. And then I'm taking the result of the ink color function and passing it back into color, or to pixels.color, which will then set the color of this thing. So basically what we're doing is we're taking the current color, passing it to this function. It's going to do some stuff, and then we're going to take the results of that and pass it back into our the color that we are then going to set on our into our buffer that we're going to send out to the LEDs. So let's scroll down to ink color.
Oh, well, where did I go?
It's down at the bottom.
Oh, I seem to have lost it. Oh, there it is. Okay.
Okay. So ink color it's short for increment color. So what we are going to do is we are going to take this color value, and this is where we do the logic of if we have the up-down flag set or not. And then we're going to either increment the color if we are going up, or we're going to decrement the color if we're going down.
Got it.
So if the color is 0, then we don't do anything. It's just we're dark. We stayed dark. We decided not to randomly we decided not to start incrementing. So if it's 0, do nothing.
Okay. And then
However,
the second part of your logic tree.
If it's not 0, then if color and a bitwise and, have you covered bitwise
We have
and?
not. No.
Oh, okay. So color, and when you have a single ampersand like that, it doesn't do a logical and in the full values. It takes each individual bit of that variable color, which is, you see uint 8. So this is an 8-bit value. It takes each individual bit and performs a bitwise and with the value up-down flag. And up-down flag, if we look at the top, is just a bunch of zeros and a 1. The value is 1. So binary 1 is, 000000001. So we've got only a least significant bit is set. So when we do a bitwise and with that, that's basically going to throw away the 7 more significant bits, and it's only going to result in the least significant bit.
Got it.
Does that make sense?
Yes, it does.
Okay. So so that's basically a way of saying I only care about the value of the least significant bit. Mm-hmm. So if the least significant bit of color is a 1, then that bitwise and evaluates to true. If the least significant bit of color is a 0, then that bitwise and evaluates to false.
Right. Okay.
All right?
Yeah.
So so if that is true, then we continue on with the logical and, which is the double ampersand. Because if it's false, then we already know that the entire thing is going to be false, and we don't bother evaluating the rest of it. So if the least significant bit of color is true and the color is less than ramp max, that means we have not finished going up. Mm-hmm. So if the up-down flag is true and we are not at our maximum ramp value, then we are on our way up that ramp. And we're going to go ahead and increment some more. We're going to do another increment.
Nice. Okay.
So if all of that is true, then we add our ramp up increment to the color variable. So we are on our way up that ramp, and we're gonna keep going up.
Keep going up.
Go back to the next code. The next one is if we have color and up down flag. So we are on our way up, but the color is greater than or equal to max. That means that we have hit the top of our ramp, and we need to make a decision to turn around and start going back down again. All right? And the way we do that is by removing the ramp, the up-down flag. So we are subtracting the value of the ramp down increment. So we start ramping down, and we also remove the up-down flag by subtracting it from the color.
Got it. Okay.
Okay. So that unsets that ramp down or that up-down flag, and now it is now an even number instead of an odd number. And so we'll start going down on our slope. English word, speakly eye, goodly eye. And then the fourth conditional there is if not color and up-down flag. So if the up-down flag is not set, then that means that we're on our way down. And so we're going to start decrementing our ramp down increment. And so we just pull that much out. Now, you'll notice I have a couple of to-dos in here. I have a couple of things in here. So we have some weird conditions of, as long as you pick your pound defines up at the top of the program correctly, your ramp up will go up by a certain amount and hit a certain value, and your ramp down will go down by a certain amount and always hit 0. The values that are in there right now, this is safe. But if I change some of those values, then my ramp up might be 5, and my ramp, I might add 5 every time, and my ramp down might be 7 every time. And you're going to end up going right over 0. And it doesn't handle the the underflow condition.
Right,
or going your way up on max, you might end up going over 255, and it won't handle the overflow condition. So there is a to-do here for our viewers to, make this code a little bit safer. I want to be able to test. I want to be able to handle arbitrary values of ramp up and ramp down and the times and all that fun stuff. Right now, I very carefully selected values that will work with this. But you can't just throw arbitrary values in there, because you'll have these weird edge conditions that won't get caught properly, and your LEDs will just start cycling through, and it will look like a blinking LED.
This is actually a great exercise for the folks at home, because not only will they need to figure out the logic for catching those, but they're going to need to figure out how they induce those.
I put it all on you. Tweet me at Smitty Halibut when you figure it out.
Fix it, folks.
Turn in your homework. That's what I want to see. I want y'all to turn in your homework and tweet me at Smitty Halibut, and tell me how you fixed your code.
Well, folks, there you have it. You have 2 different ways to use an embedded processor to control WS2812 LEDs. One of them uses, pretty standard bench format. This is an Arduino Uno, and Smitty, of course, did it on a much smaller, and this is why it's more challenging, a much smaller embedded processor to make himself a twinkling ring. What we want you to do is we want you to take what we give you, the links for these devices, so you can order the hardware. And remember, this hardware is inexpensive. You can get the entire setup that I've got on my bench for about $20. Smitty, how much did your hardware cost?
Oh, great gravy. The ring of LEDs, I think, was about $16 on eBay. I think Adafruit sells it for a little bit more than that, but it's made in the U.S. and probably better quality. You were worried about quality of LEDs.
Yeah.
I can guarantee you that Adafruits will not be a problem.
Yeah, that $10 LED ring isn't such a bargain when it doesn't really work.
When you have to buy 5 of them to find one that works.
Exactly.
And then these DigiSparks are pretty inexpensive as well.
Oh,
so,
yeah.
Yeah,
Well,
I don't remember how much these were, but they're, I think, $8 each, less.
And I will say, the embedded processors that are on these little rings, they are capable of controlling much more than just the I can't get it over there. They're much more capable than controlling just the LEDs on the ring. So if you wanted to start off with something like this, again, you can daisy chain off of this to control more lights. You can control sticks. You can control rolls. In fact, I just bought a roll of it's the super high density 2812s, so that I can set them up into an array. I'm going to make a big wall of these things and see if I can do some animation. But we want to see your projects, and that's your homework from this episode of Coding 101. Smitty.
And fix my bugs.
Fix our bugs. Smitty, I want to thank you so much for being part of this episode. Could you please tell the folks at home where they can find you? Of course, I think the best place to find you is at DEF CON. Go get the experience, go there. But that's not until August. Until then, where can they find what you've been working on that's not under a non-disclosure agreement?
I look forward to being able to talk about that one at some point too.
At some point.
Yes, Twitter is really the only place I spend on the social webs. I don't do Facebook. I don't really do email a whole lot. Grab me on Twitter at Smitty Halibut. It's down here on my lower third. Over there we go. And at Smitty Halibut, find me there and talk to me about what you guys are doing. Show me your stuff. I would love to see what you guys are working on, guys and gals. I'm always interested in hearing what kinds of cool things people are doing.
Yeah. Again, a pleasure. I will work with you every chance I get because it is just so much fun.
Thanks
folks,
for having me on, man.
Yeah, we will hopefully have Lou Maresco back next week. The reason why he's not on this week is because he's currently on paternity leave. He's got a baby coming, and
Nice.
I understand they don't schedule really well. So,
No, they don't. Mine came 4 weeks early.
He emailed me last night. He goes, "We've had 3 false trips to the hospital already." I'm like, That's just how that works. That's why I prefer to deal with code. But hopefully we'll have Lou back. If not, I'm going to just keep inviting Smitty, because if Lou's not here, I'm going to do something I really, really enjoy. We'll do something else on an Arduino. But don't forget that you can also find me on Twitter, twitter.com/PadreSJ. It's a great place to find out what we're going to be doing on every episode of Coding 101 and to suggest projects, both for this show and the other how-to show that I do, Know How, with Brian Burnett. Also, thank you to everyone who makes this show possible. Of course, that's Lisa and Leo, who let us do Coding 101. That's Smitty Halibut, that's Mark Smith. It's Lou Maresca, normally when he's not dealing with babies. And my TD, Anthony. Anthony, do you have a camera on yourself?
Yes, I do.
Can you say hello to the folks?
Everybody.
Because you do so much work in the background, and we never say thank you.
Thanks.
That's it. That's all.
Yep.
By the way, he's definitely afraid of
Thanks,
cameras.
Anthony.
Yeah.
You're welcome.
Until next time, I'm Father Robert Ballister. This has been Coding 101. And as we say, end of line.